Alright, hello, welcome back. In the last video I told you about the method of reduction of order, and that was great, except it required that your differential equation come with one solution already. And the question is, well, what if we were looking at something that looked pretty much the same, but didn't come with a particular solution? And I'm going to show you a technique to deal with what we're going to call Euler equations, which are equations of the form t squared y double prime plus some number of t's times y prime plus some other number of y's is equal to 0. So it's second order and linear, it's homogeneous, but it does not have constant coefficients. But it has coefficients that are, very predictable. And so what we're going to do is we're going to start off with a little change of variables. We're going to kind of solve this in general, and then I'll work a couple examples for you. But overall, I think that this should be a pretty friendly technique to us. So what I'm going to do, I'm going to start off by letting x equal the log of t. Okay. Now I'm going to need to find formulas for y double prime, y prime, and y in kind of an x world after we've made this transform, let x equal log of t. Okay, and because really what I'm looking at here is y double prime of t, y prime of t, and y of t. But I want this to be a differential equation in x. So what I'm going to do is I'm going to say, well, the first thing it's pretty obvious is that dx dt is going to be 1 over t. All right? And, well, I know that if I want, I'm eventually going to want y of x, y prime of x, and y double prime of x. Y prime of x, that's dy dx. And I think this will make it a little easier to see where I'm getting this idea from to make this substitution. So dy dx is going to be, wait, hold on. I may have wanted to say, no, yeah, I want to say dy dt because that's what I've got and I'm working with. So it's what I'm going to want to substitute on also. Okay. So dy dt is going to be dy dx times dx dt. And so that's dy dx times 1 over t. Okay. And I'm also going to need a formula for y double prime of t. That's the second derivative of y with respect to t both times. So what I'm going to do is I'm going to have to take the derivative of this with respect to t. And we can do the product rule on this. This is definitely within our grasp. So it's going to be, first I'm going to take the derivative of this, and I'm going to leave 1 over t the same. Times 1 over t. And then I'm going to add in, leaving dy dx the same, the derivative of 1 over t. Well, that's t to the negative 1. Its derivative is negative t to the negative 2. So I'll have minus dy dx times 1 over t squared. Now, what's going to happen when I take the derivative of dy dx with respect to t? I found this, I was thinking through this when I was making my notes earlier, and I was thinking through it, and I was like, oh man, as far as the using this type of notation, I'm not exactly seeing what's going to happen. So what I did was, let me just grab a different color, I got yellow here, was I said, well, dy dx is y prime of x, right? But x is a function that depends on t. So y prime of x of t. So if I'm going to take the derivative of this with respect to t, okay, well, I'm going to get Okay, I'm going to take the derivative of the outside while leaving the inside the same. And then multiply by the derivative of the inside. Well, that's x prime of t, dx dt, whatever you want to call it. And this is second derivative of y with respect to x both times. So I'm going to say that I have second derivative of y with respect to x both times dx dt is 1 over t times this 1 over t is going to be a second power of t in the denominator. So I'm going to, because I think I'm going to need to, I'm going to need to move over to that side. I'm going to probably collapse all this down into, all right, I have second derivative of y on x both times 1 over t squared minus dy dx times 1 over t squared. And I'll be erasing this computation. All right, and now what I'm going to have to do is I'm going to substitute dy dt here and second derivative of y with respect to t both times right there in that equation. So I'll have, what is it going to be now? After the transform, I have t squared times y double prime, and y double prime was second derivative of y respect to x both times 1 over t squared, that's promising, minus dy dx times 1 over t squared. Is it plus alpha t times y prime, and y prime was dy dx times 1 over t. Plus beta times y, well, that's just going to become y of x after the transform. And that's equal to 0. So I'm going to distribute this t squared to both of these, and so I'll have a, and I think at this point, to kind of save some time as I'm writing this out, I'm going to start calling this y double prime of x and this y prime of x. Okay, so I've got y double prime of x, once I'm divided by the t squared. T squareds are going to cancel again, minus y prime of x. Okay, here the alpha, or not the alpha, but the t divided by t, that's going to cancel, and I'm going to have plus alpha y prime of x plus beta times, maybe I'll call that y of x equaling 0. Okay, now if I combine this, I'll just have alpha minus 1 here. So what this has become is a second order linear ODE in y of x that has constant coefficients, and we know how to deal with that, all the different ways that can play out. Plus beta y of x is equal to 0 now. Okay. Yeah, and then, so we know how to solve this. We go to a characteristic polynomial, right? This is going to be, go to r squared plus alpha minus 1r plus beta r is equal to 0. That's going to give you r1 and r2. What was I going to say about that? Oh, yeah, and we know what to do if r1 and r2 come back as complex conjugates. We're going to use sine and cosine. We're going to know what to do if they come back repeated also. And of course, in the case where they come back distinct, it'll be, e to the r1, c1 e to the r1t plus c2 e to the r2t. And that's true in general, even if they are complex. It's just you have to dive into what does that mean in terms of cosine plus I sine. So let's just say we get r equals r1 and r equals r2 are our solutions. And I will say right now I'm just supposing they're distinct, although I think you will know what to do if they're not. Then we get y1 equals c1 e to the r1x, right? Because this was a second order ODE and x. And y2 equals c2 e to the r2x. But x is equal to log of t. So what I'm going to do, I'm just going to leave this here. But I think that you can see how once I substitute back in on x equals log t, this is going to be good, right? Because I'm going to have an e to the log t, that becomes a t, and oftentimes these things just come back. The solutions are just powers of t. So plus c2 e to the r2 times log of t. I think now would be a good time for me to jump in and do an example. Okay, so here you go. Got t squared y double prime minus 4t y prime plus 6y equals 0. Okay, using the results from before, what we're going to do is we know that this goes down to basically, what would it be, y double prime of x minus 5t y prime of x plus 6 times y of x equals 0. And that's because when I went through all of that, what the original Euler equation boiled down to was y double prime of x plus alpha minus 1 y prime of x. Okay, so alpha was -4, and maybe I'll actually write that in. Alpha equals -4 and beta equals 6. And so it was y double prime plus alpha minus 1 t y prime. Wait, no, there's no t there. Pardon me. Alpha minus 1 y prime plus beta y equals 0, where this is y as a function of x. And well, we know that this goes to the characteristic polynomial r squared minus 5r plus 6 equals 0. So that gives me r1 equals 3 and r2 equals 2. Okay, when I factor and solve. And so my solutions are going to be y1 is c1 e to the r1x, okay, so that's e to the 3x, and y2 is c2 e to the r2x. And we know that x is equal to log of t, so I'm going to say that y1 of t is equal to c1 e to the 3 log t, and y2 is c2 e to the 2 log t. Okay. Whoops. Let's say that y2, point out that it was a function of t. Okay, so my general solution is going to be these added together. But I would prefer for you to know that, wait a second, I know that, 3 times the log of t is the same as log of t times 3, and I could use an exponent property to say that this is e to the log t. Maybe I'll write this down once. All right, using that exponent property where I can, reverse the order of the multiplication and then kind of block it off, that's t to the third. Okay, so c1 t to the third plus c2 t to the 2 is going to be my general solution. Now I've got one more example for you that's going to come back with characteristic polynomial will come back with complex roots. And I'll show you how to deal with that. It's really not going to be any different from what we did before. We're just going to have to throw in a log t where before we had a t. Okay, so That's t squared plus 7t plus 10. So. So this one, okay, I'm going to do the exact same thing, right? Alpha equals 7, and beta equals 10. So, the beta's not going to change. Alpha's going to get decreased by 1. The t's are going to go away. That's really what's going to happen here. So I've got, where am I? Oh, yeah, y double prime of x plus 6y prime plus 10y is equal to 0. So that's r squared plus 6r plus 10 equals 0. All right, b squared minus 4ac is negative, meaning this is going to come back with complex roots. Okay, me personally, rather than using the quadratic formula on complex roots, I prefer to complete the square. Okay, so what I'm going to do is I am going to, hold on, what am I going to do here? Oh, yeah, I'm going to say, like, what would be the square here? That would be r squared plus 6r plus 9. So I need to subtract 1 from both sides of this equation. So r squared plus 6r plus 9 equals negative 1. And I'm probably just going to do the algebra, erase it, and then put it right back up here. So that's r plus 3 squared equals negative 1. And take the square root of both sides, and that's going to be, really the absolute value of r plus 3 equals I. Right? But we're going to just say plus or minus I. And then I'll have r equaling negative 3 plus or minus 1i. So yeah, I'll just say over here, negative 3 plus 1i, and r2 is negative 3 minus an i. And what we knew to do in that case was, if we had, a plus bi, the a was what went as the as the kind of coefficient of t in the exponential, and the b was what went in the trig. Okay? So what we're going to do is remember that this is y1 of x. y1 of x is going to be, well, c1 e to the negative 3x times the cosine of bt. I mean bx in this case, so it would be cosine of 1x. That's what I'm trying to say, cosine x, then, well, I guess I'll just put it separately, y2 is going to be c2 e to the negative 3x times the sine of 1x, because this was 1i and negative 1i. All right, times the sine of x. All right, and we know that x is equal to the log of t, so we're just going to make that happen here. Okay, so y1 of t is going to be, okay, c1 t to the negative 3 times the cosine of log of t. Well, that's, oh wait, no, that's not the, I was like, that is an unusual function, but it's, kind of like the antiderivative of tangent, but that's not the case at all, right? That would need to be log of cosine, I think. Or maybe that would be negative tangent, or something related to the arc, or the antiderivative of tangent. Okay, but it's not, because this is the cosine of the log. And then y2 is going to be, c2 t to the what's going to happen? Oh, t to the negative 3, yeah, thing, sine of log t. And so my general solution is y equals this plus that, add the two of them together. And this is how we're going to deal with Euler equations, which, you probably won't have to deal with too many of them in this class, but this is just a technique that we can really, in general, deal with this. It's solved, right? We've got it completely boxed in. We'll be able to deal with any of these. And so now, at this point, the method of reduction of order, I'm probably going to give you problems that are going to look a little different from the Euler equations, because this is a nice shortcut for that. And in the next video, I'm going to be telling you about the method of variation of parameters, which is going to be another way that we can solve a linear second order ODE.